Good?
Yeah.
All right. Okay, guys, thank you for coming. This is supposed to be our last lecture in the flight dynamics course. This year, I decided to make this lecture a bit different. Yeah, thanks. Professor Boswell is joining us. I decided this year to make this lecture a bit different in the sense that, I just finished a study of the history of flight mechanics and flight stability. So I thought I should share it with you. And I invited some people from outside the class. Mostly they are on Zoom. So as you know, I'm very interested. Is it good enough now? Perfect. I check. So as you guys, I don't know if you know, but I'm very interested in the history and philosophy of science. I have done some studies before and summarized them in several lectures online. One on the history of mechanics, one on the history of the beautiful principle of least action, one of the history on fluid mechanics, aerodynamics, and the nearest and dearest to my heart is the history of the theory of lift, a mathematical war in the background of the Great War. Highly recommended, much more interesting than today's talk. You can access any of these talks on the YouTube channel UCI Dynamics or on my website. Today's talk is on the history of flight stability, control, and flying qualities. So today's lecture is about history of flight stability and control. Basically, this particular question, how did it become obvious that an airplane should be inherently stable? And the usual disclaimer, like all my endeavors, this is not any different, far from being complete. It's actually almost impossible to combine all the interesting stories and concepts in a single lecture. So this will be simply a hodgepodge of concepts and things from here and there. Hopefully they will form a story. So my sources are David Bloor's masterpiece, Enigma of the Aerofoil, highly recommended to every single aeronautical engineer. This is the book that I summarized in the mathematical war talk. But today I'm relying more on Vincenti's book, What Engineers Know and How They Know It. Also some material from von Karman's book in aerodynamics, in addition to a wonderful collection of interesting papers, Melvin Goff, Notes on Stability from the Pilot's Standpoint, Otto Koppen, Airplane Stability and Control from a Designer's Point of View, the 1984 Wright Brothers lecture by Harper and Cooper on handling qualities and pilot evaluation. And in fact, Vincenti had an article on the exact same title. How did it become obvious that an airplane should be inherently stable? Okay, so let's start. This is the beginning. As you guys know, December 17, 1903, the Wright brothers made their historic record of the first powered flight, but there was no guiding principles, no theory to answer the simplest questions in aeronautics, like how we compute lift on a wing, how we assess the flight stability of an aircraft. Basically, the Wright brothers, they built their airplane by trial and error, relying on their engineering ingenuity, amazing hands skills. And this is clearly can be seen in a letter by Lanchester. Let me have this laser pointed. To Colonel Fullerton, the honorary secretary of the Aeronautical Society, he wrote to him saying, I think it was a mistake of the Aeronautical Society giving the Wrights a medal for their contribution to aeronautical science. I agree with their having the medal, but it should have been for what they have done. So meaning, of course they deserve a medal, but they contributed nothing to aeronautical science. One of the interesting incidents at the time was the first cross-channel flight from France to England by Louis Blériot. So newspapers in England came the next day saying, with headlines, Britain is no longer an island, the nation's basic line of defense is breached, the channel is no longer a moat that makes the island impregnable fortress. So as you can see from these dates, there was already a political tension in Europe, and the emergence of a new machine that could change the course of an impending war, it made the situation even more inflammatory. This was clear actually in the language of and the tone of scholars themselves. So here is George Bryan saying, the Germans are probably putting their best brains into improving their aeroplanes. In the words of Greenhill, his 1914 Nature paper, he described it as a mathematical war. So right before, during, and after World War I, there was a parallel mathematical war between the Cambridge School of Mathematical Physics from one hand and the Applied Mathematics and Engineering School in Gottingen, on the other hand, to develop two theories, one for lift and one for stability. The Germans won the mathematical war on lift, and this is why you see names like Kutte and Prandtl dominating our undergrad textbooks in aerodynamics, how to compute lift and wing theory. And this war, particular war on the theory of lift, is expressed in details in this amazing book. I really highly recommend it to every single aeronautical engineer. And this is the book we summarized in the talk on the mathematical war. On the other hand, George Bryan, an applied mathematician from Cambridge, he managed to develop a successful theory for stability. And this is the talk of today, actually. So this is George Bryan. He's probably the most important character in the history of flight stability and flight mechanics. He was, like I said, applied mathematician, came from Cambridge, got interested in aviation in the early days. Here is one of his first papers on the topic. In Nature, 1909, under the title Aviation. In this paper, he counted many accidents due to failure in understanding stability. And this is what he wrote. The obvious remedy is that aviators should wait until this subject has at least been thrashed out mathematically. Of course, this is funny because engineers would never wait for a mathematician to solve the problem, right? They have to move on. Most of the work was developed in a Nature paper 1910 under the title Aeroplane Stability. He considered the plane as a rigid body, wrote down the equations of motion, focused on the longitudinal plane, linearized the equations of motion about a reference point like cruise to study the dynamics of small disturbances from the reference point. And he asked the ubiquitous question, given a small external disturbance, will the airplane come back to its equilibrium so the disturbance will die out eventually, or it will diverge? And he found that the answer lies in the roots of a quartic polynomial, a fourth order polynomial, what we call now characteristic equation. As you guys can see, this is the longitudinal plane. It's the 4x4 system. So we have fourth order polynomial. So for you, as some people who attended this class, you can recognize that this is precisely the exact same procedure that we follow after more than 100 years after Bryan, which really points to his lasting impact on the field and visionary endeavor. Another interesting point is that if you're someone who attended this class and you look at these coefficients of the polynomial, what do you think they are depend upon? If you think a little bit, you're going to realize that they should depend on the stability derivatives of the airplane characteristics. And indeed, yes, so A in particular depends on the damping derivatives. And how we get these stability derivatives in this class, if you remember? Well, we rely on our basic understanding of aerodynamic theory. For example, for MQ, we apply a pitch disturbance Q and see the change in the angle of attack on the horizontal tail. And because we have an aerodynamic theory in the sense that we know now that the change in the lift coefficient is simply equal CL alpha, the slope, times the change in the angle of attack, right? But interestingly, there was no aerodynamic theory at the time. So ironically speaking, the flight stability theory was developed before the aerodynamic theory, which doesn't seem to be the right chronological order, but this is really typical in history of science. The scientific discovery is almost never linear path, straightforward path. It's usually highly nonlinear, tortuous. So George Bryan lumped all this analysis in a detailed book called Stability in Aviation, 1911, submitted to Nature, and it got declined. So the most foundational work in our domain, in flight stability, that is currently being used in every single aeronautical engineering school throughout the world, every single research and design office throughout the world. This foundational work was declined not once, actually twice. Interestingly, back in the days, the reviews used to be published, and the reviewers used to sign by initials. So the reviewer who rejected this paper signed by WHW. And people guessed that this must have been Sir William H. Wright. Interestingly, there was a heated discussion between William Wright and George Bryan earlier on a topic that is, very irrelevant. It's on the division between mathematicians and engineers and blah, blah, blah. We're not saying that this was the main reason behind the rejection of this paper, but unfortunately, this is something, that we we see in academia. It's not uncommon that disagreements and heated discussions about different topics can lead to rejections of papers and proposals. This is something that we academicians should strive to minimize. But anyway, one of the main criticisms of Bryan's work is that it's not practical. Here is how people mocked him. Designers could not wait for the solution of a differential equation or its determinantal quartic. I don't know what they are talking about. So they don't like solving a differential equation, but they are perfectly fine of flying an airplane without doing stability analysis calculations and jeopardizing or sacrificing a couple of airplanes being crashed and the lives of some people, and because they prefer this over solving a differential equation. I mean, it's not understandable to me. The paper was declined at the Mathematical Gazette as well, and the reviewer wrote the following: the author is obliged to make a series of assumptions. That the air resistance, they mean the aerodynamic forces at the time, are linear functions of small changes in linear and angular velocities. They are proportional to the square of the velocity, v squared. They are normal to the planes, meaning he's ignoring drag contribution and focusing on lift contribution only. Proportional to sine alpha, and taking alpha as small. And then the reviewer, he concluded, or I don't know, I don't know the reviewer, maybe she, the cumulative effect of small inaccuracies in each assumption may be considerable. So it seems very, this is a legitimate concern, really. I mean, if you think about it, if you have a small error in each assumption and then you add up, so at the end of the day, the final result may come out as irrelevant. But the interesting point is that people sometimes really forget about the very nature of our science, is that there is no equation, there is no mathematical model, there is no theory that is ever complete. There is no such a thing. They are all idealized mathematical models, including the so-called governing equations, Newton's equations, Navier-Stokes equations. They are all idealized models. And in fact, the main strength of an academician is to identify the smart assumptions that are both, they should be reasonably accurate, so you don't lose much by adopting them, and at the same time they are enabling, they allow you to do analysis that you could not do otherwise. And if you look here at these assumptions, and you're someone who's taken this class, these are the exact same assumptions that we're doing, like linear aerodynamic changes in the aerodynamic loads are linear functions of the angular velocities, PQR. Right? They are proportional to the square of the velocity, v squared. All the aerodynamic loads are proportional to v squared. Ignoring drag contribution, focusing on lift contribution because the very large lift to drag ratio. And one of the most interesting to me, frankly speaking, is that he considered that aerodynamic load is proportional to sine alpha. We nowadays take it for granted because we have an aerodynamic theory. So the lift coefficient on a flat plate, we know very well, it's CL equals 2 pi sine alpha, so that's very well known. At the time, there was no aerodynamic theory. And indeed, in Britain itself, the dominant aerodynamic theory at the time, which was the incorrect one, it had a complicated nonlinear dependence on alpha. It was not sine alpha. Indeed, this is something that skipped historians. People did not comment about it. For me, it's amazing. I don't know how he came up with the sine alpha dependence, really. So some other people criticized his work on the basis that one of the excellent airplanes at the time, BE-2 in England, it was already highly stable, and it was designed to be stable, made stable by trial and error, not relying on his analysis. So we don't need your analysis anyway. We can design stable airplanes by trial and error. Yes, but he's providing some mathematical tools that can save time, money, effort of the trial and errors. Another criticism was, well, stability is not everything. The community learned that stability is usually in conflict with maneuverability and controllability, and in particular, the British community, they learned it the hard way. So here is one of the incidents happened in the early days of World War I. They call it Fokker Scourge. Anthony Fokker, he built this airplane for the Germans. It has a forward-firing machine gun that is synchronized to fire through the propeller blades. And so that was quite an innovation at the time, but also the airplane had a mono wing. So it was less stable but more maneuverable in comparison to the British biplane, highly stable BE-2. So during summer 1915, there was high air superiority of the Fokker airplane in comparison to the British airplanes, leading to the loss of many airplanes and many lives, unfortunately. So people at the time, they were well aware that stability is not everything. We have other metrics like maneuverability, and your analysis, Brian, does not give any clues about maneuverability, so it may not be useful. One of the most interesting criticism, to me, in my perspective, frankly speaking, is this one. That it's only applicable to small angles of attack. And this is, oh my goodness, we are 114 years after Bryan's, and there is no systematic way in the community to analyze stability at high angle of attack. And this attitude, you see it, you see this attitude over and over again in the history of science. Someone comes with a new concept, a new theory, people got excited, but then they criticize, saying, but your theory or your concept is not applicable here or there or there. It's like actually, this happened to me personally. We develop, we teach aerodynamics in, undergrad, and we know how to compute lift for a two-dimensional airfoil with a sharp edge, small angle of attack and everything. We did a little bit of generalization to generalize this to arbitrary shapes, those that do not necessarily have sharp edges. And then some people got excited, and others say, well, but your theory is not applicable to high angles of attack, it's not applicable to reversed airfoils, but so does the classical theory. I mean, we have our own little piece. So let's go back to Bryan's story. The point is, yesterday before Bryan's work, the community did not have any means to assess stability for small angle of attack or large angle of attack. Airplanes were crashed like crazy. So why you guys don't adopt this mathematical analysis, make use of it to design safer airplanes, and then move together as a community to the next step? So it's this behavior, I observe it several times in the history of science, and frankly speaking, I don't have any explanation for it. Luckily, a colleague of George Bryan, here, Bairstow, he got excited about Bryan's work, and he put it upon his shoulders to check it experimentally in the wind tunnel. So he did some wind tunnel measurements at the National Physics Laboratory over a couple of years with the help of Melville Jones. So they had to measure stability derivatives in the wind tunnel because there was no aerodynamic theory to estimate stability derivatives. So you can imagine they changed the angle of attack and measured the changes in the aerodynamic loads. They apply a pitching angular velocity Q and measure the changes in the aerodynamic loads. This was in 1912. Really a heroic effort. Once they have stability derivatives, they can substitute in the fourth order polynomial, the characteristic equation of Bryan, to get the eigenvalues, the modes, and compare the oscillations of these modes against the oscillations that are measured and observed in the wind tunnel. And they found good matching, which gives an experimental stamp to Bryan's pioneering analysis. Over the next couple of years, there were similar experiments at MIT by Hansker, leading to similar results, confirming Bryan's stability analysis. So this has led to a happy end, quick happy end. Bryan received the gold medal from the Royal Aeronautical Society. After this point, we as a community, we now know how to assess the stability of a given aircraft. But the question remained, do we need stability? Should we design our airplanes to be stable? And if yes, how much stability do we need? Can you? Yeah, let's mute. How much do we need? How much stability do we need? So I'd like to go back to this point of the contention between stability and control and demonstrate it on a simple example. This is the example we considered several times in this class. An airplane model in the wind tunnel mounted on a hinge that allows the airplane to freely pitch up and down. So you can easily write down the equation of motion for this single degree of freedom system. Theta is the pitching angle, delta E is the elevator deflection, as you guys know. You can get the transfer function, it's a second order system, and if you apply a step change in the elevator deflection, like the pilot pulls the stick 1 degree or something, here is how the airplane will respond in the pitching angle. Of particular interest is this value of the steady state pitching angle, right? And the question is, if the pilot gives 1 degree elevator deflection, how much theta steady state do we get? Do we get half a degree? Do we get 5 degrees? So this represents, or gives you an indication about the sensitivity of the airplane, the control authority of the airplane, right? Interestingly, the control theory tells us that this value is precisely dictated by the DC gain of the transfer function, which is we easily get by setting S equals 0 in the transfer function. If we do that, we get the DC gain to be M delta over M alpha. And as you guys know, M alpha is our stability metric. It's our spring constant, pitch stiffness. So higher M alpha means higher stability. So as you can see from here, simply higher stability implies smaller sensitivity and weaker controllability. And this was not confined only to the pitching motion of the airplane. This was also in the yaw dynamics. You can get a very similar expression. Simply replace the pitching moment M with the yaw moment N, delta elevator with delta rudder, angle of attack alpha with the side slip angle beta, and you get a very similar expression. So likewise, larger weathercock stability implies weaker controllability or weaker sensitivity of the airplane. And in fact, in the early days, this was quite serious. So here is Melvin Goff, test pilot, saying, in all airplanes tested thus far, the stability in yaw has been observed to predominate so strongly as to overcome the rudder effect that the pilot can exert. So in these airplanes, the pilot gives a rudder pedal, but the airplane resists immediately, and the end result is very weak shift in the yaw dynamics of the airplane, in the yaw output. So we talked about this in the class several times, right? So a too stable airplane will vigorously reject and resist disturbances, and it will not distinguish between a disturbance that is real disturbance, right, coming from the surrounding environment, and a disturbance that is coming from the pilot in the form of a command or a maneuver. So it will reject both in the same way. So that's the issue here. So you can imagine that this actually triggered 2 schools in the community. Here is Turner in his book, Aerial Navigation. He wrote, the question of how to obtain equilibrium has developed into controversy, dividing aviators into 2 schools. One school holds that equilibrium can be made automatic to a very large degree. The other, known as the American school, following the methods of the brothers Wright, claims that equilibrium is a matter for the skill of the aviator who, with practice, acquire perfect control of his machine. So in the words of Gibbs Smith, a historian aviation, had an interesting book, Aviation and Historical Survey from its Origins to the End of World War II. He described the proponents of the first school, stability school, as chauffeurs, and the proponents of the second school as airmen. So to chauffeurs, airplane is simply a winged automobile. The pilot role is only confined to steering, guidance, but not to stabilize the aircraft. The aircraft should be stable on its own. This school dominated in Europe and came out of century of tests of hand-launched models by people like George Kiley and Lanchester and others. And if you think about it, it makes perfect sense, because if you are designing an airplane that's going to be hand-launched, so it will fly on its own, you will not be on board to control the airplane. So the airplane will fly by itself. It has to be inherently stable on its own, right? So that makes sense. Speaking of Lanchester, I'd like to digress a little bit. I'd like to touch upon his story, because he has an inspiring story, frankly speaking. Lanchester, he wrote 2 books in aviation, the early days, one on aerodynamics and one he called aerodynetics. In this one, he came up with a famous criterion, CM alpha being negative, so he is the one. And he also discovered the long period mode. And this also makes sense because once he launched a hand-launched model, he always observed that the airplane goes into these oscillations, which we discussed in class as the airplane goes down, speed increases and lift increases. And at some point, the excess in the lift pulls up the airplane into a climb. As the airplane is climbing, the speed decreases, lift decreases. And at some point, the decrease in the lift pulls down the airplane. And the airplane keeps oscillating in a long period. So these oscillations take long period. In fact, he did some mathematical analysis to correlate the frequency of these oscillations to the initial speed of the launch. which is quite interesting. And this was well before Bryan's analysis, all right? But the community actually neglected him, did not accept his contribution. Unfortunately, he did not belong to the elite group of Cambridge mathematical physicists and applied mathematicians. He was a practical engineer. He had actually an automobile company. So even in the words of Bryan described his work saying, his work certainly appears wanting in rigor. So they saw his work as not rigorous enough, so they just ignored him, unfortunately. It's quite sad because Lanchester made several contributions across domains in aviation, from 2D, 3D wing theories, even boundary layer, static stability CM alpha, dynamic stability long period, but the community really, they sided him. It was a sad story. Personally, I believe this was the main reason behind his naming long period as phugoid mode, because as we saw, the long period mode is really natural in flight. Whenever he launches a model, it goes through these oscillations. So he felt like the long period mode is intimately associated with flight. So he wanna give it a name that means flight. But because they looked down at him as someone who's not elite enough, I think that he wanted to show that he is a better educated person, so he picked a Greek word meaning flight. So phugoid is a Greek word meaning flight, but ironically, as you guys know, it doesn't mean flight as we know, it means fleeing from a threat. It's like fugitive, which became the standard name of long period mode. So yes, the standard name of one of the standard flight modes in aviation was named by mistake. Luckily, the story had a happy end after 2 decades, 20 years or something. He received the gold medal from the Royal Aeronautical Society. So let's go back to our division in the community between the two schools. The second school focused more on control than stability. This school was pioneered by Otto Lilienthal in Germany and the Wright brothers in America. And also, it made sense when you think about it because they used to fly gliders by themselves. So if you think about it, if you are building an airplane that you're gonna fly yourself, it is quite instinctive to build it in a way that gives you control authority over the airplane, right? You really don't care about stability. And indeed, historians of aviation, they reached consensus that the Wright brothers' focus on control over stability was the main reason behind their success of achieving the first powered flight, indeed. But this means that if the Wright brothers' airplane was flown in Germany, not Germany, I mean in general, in Europe, by European pilots who were not used to these kind of unstable airplanes, they would feel uncomfortable and they would describe it like crazy unstable. And indeed, this came out in 1920 report in the Advisory Committee for Aeronautics by one of the test pilots. He flew the Wright brothers' airplane and came back saying, it needs equilibrist of the first order to maintain a stable flight. It's like, this is a crazy airplane. Interestingly, when you look at this picture, I cannot help but remember the fundamental difference, the current fundamental difference in design philosophy of flight control systems between the American Boeing school and the European Airbus school. As you guys know, the Boeing school allows more authority for the pilot than the Airbus school. On the other hand, the Airbus school, they allow the pilot to rely more on automatic systems. So I'm not sure if this current division is reminiscent of this schism back in the days. I don't think so. There is quite this a disconnection in time, but it's the similarity is unavoidable. So I think it's interesting for someone to trace if there is any link or not. There was a paper in 1985 that dedicated to assess the handling qualities of the Wright brothers, and Jackson and colleague, they wrote that the Wrights did not understand stability in the precise sense that we do now. They could not formulate precise ideas of stability in contrast to equilibrium that we stressed in this class. Whether their aircraft were stable or unstable was an accidental matter. And this makes sense because the Wright brothers did not receive a formal education. They were amazing tinkerers, inventors, great hand skills, but I think to formally and rigorously formulate the stability problem, this was something like out of their reach. In fact, Perkins, in his von Karman's lecture, he wrote, until the pilot has experienced it and can anticipate and control the behavior of his machine in the air, he cannot decide what is necessary or possible to leave to the automatic mechanisms and built-in qualities. So, as you can see, I mean, really the philosophy of the Wright brothers, whether they thought about it in a deep way or not, or just instinctively, to focus on control was very useful for the community, because at the end of the day, if you want to design an airplane or whatever, you want to know, you want to learn what that can be handled by the pilot and what that must be handled by the design of the airplane. So there has to be someone who tries and tells us, you know, what can be handled by the pilot and what cannot be handled. Vincenti wrote that only after Wright, the Wilbur Wright's masterful demonstration of controlled flight in France in 1908, not only to achieve effective stability but to initiate maneuvers, did the European philosophy begin to change, which makes sense. If the only successful airplane of the time was unstable both longitudinally and laterally, it will trigger the question that do we really need stability? Vincenti also had a nice comment on this. He said, a normal bicycle, though inherently unstable at low speeds, is ridden with ease by millions of riders who supply stability by corrective action. Without being conscious, they are doing so. Which makes sense. And in fact, if you remember back in the baby days when we learned how to bike with the so-called the training wheels, they provide stability, right? But once we learn how to bike, we immediately trash them away because it cripples the performance of the bike and the maneuverability of the bike. It's not really fun to bike with these wheels. So, and we're perfectly fine with the instability, right? So the same for pilots. A fighter pilot may be perfectly fine with an unstable aircraft, but he or she would want, you know, command and control over their vehicle. So this actually initiated a debate on the necessity of stability in the community that remained open for decades to come. On one hand, you will find people like Bairstow and Jones saying something like, while some may still be found to dissent from this view, meaning stability, it will at least be conceded that instability is clearly a disadvantage, that a machine flying in still air should tend continually to depart from the condition of normal flight and require the constant attention of the pilot to bring it back to the correct attitude will hardly be urged as a characteristic in general desirable. On the other hand, you will find people like Hansekar at MIT saying something almost completely opposite. It's well known that the French monoplane pilots demanded at one time a neutral aeroplane with no stability whatever against pitching, on the ground that stable aeroplanes were too violent in their motion in gusty air. This is quite interesting because it's a bit counterintuitive, because one might think that a stable airplane should do well in turbulent and gusty air. That's, you know, seems to be that's the role of stability. Actually, on the contrary, because as you guys know, too stable airplane will vigorously resist and reject every single little disturbance. So in a rough air, in a turbulent air, it will try to, you know, reject this disturbance, reject that disturbance, so it will keep oscillating and lead to a rough ride. In contrast to, you know, a weakly stable airplane, which is not that sensitive to disturbances, it doesn't have this, you know, ability to resist every single disturbance. It will simply filter out these high-frequency disturbances. Hansekar said, safety in flight may well depend more upon ease of control than upon stability. The almost universal prejudice among accomplished flyers against so-called stable aeroplanes appears to have a rational foundation. In their report, NACA report 1921, Norton and Allen, they said, generally speaking, a pilot does not know a stable from an unstable machine. And if the forces on the controls are small, he is just as well satisfied with the unstable one as the other. The beginner learns to fly as quickly in an unstable machine as in a stable one. So they are referring to an interesting point that, you know, the instability of the airplane may not be directly felt by the pilot. So the community now is started to learn about the term handling quality, which is related to the pilot feel. And this is something that does not equal stability or instability of the airplane. They are different. So in fact, the term handling quality or flying quality came out in an official report for the first time in 1918 under the title Trials of Flying Qualities. At the beginning, there were some flight testing at NASA, Langley, to learn about these flying qualities. They tested 2 airplanes, and they learned that this CM alpha thing is not actually, cannot be measured in flight, cannot be observed in flight. We cannot measure the moment coefficient in flight. So that's the issue. So they wanted to come up with a different metric that can be observed in flight. So they proposed these metrics. Instead of the slope between moment and angle of attack, CM alpha, they proposed these slopes. Slope between the change in the elevator deflection with respect to speed. As you guys know, if we change the speed of the airplane, this will change or require change in the angle of attack for balance. And this will in turn require changes in the elevator deflection for trim or balance. So they are proposing this as an alternative slope that is representative of stability. Equivalently, the elevator deflection is proportional to the stick force in the hands of the pilot. So here is another metric, this slope. So let's talk about this in a moment. This is the moment coefficient. We played a lot in this class. Cm is 0, dCm by dCl CL plus Cm delta delta, and this must equal 0 for balance, right? Now from this you can get how much change in the elevator deflection per changes in the CL. This is precisely your midterm problem, right? And then you can recall the other balance equation, lift equal the weight, 1/2 rho v squared SCL. So from here you can get how much change in the CL per changes in speed. That's easy. And you can use the 2 relations to write down how much changes in the elevator deflection per speed. And you can see that this slope is proportional to CM alpha directly. So the larger CM alpha, the larger this slope. But unlike CM alpha, this can be observed in flight. We can measure the elevator deflection in flight. We can measure the airspeed in flight. So that was a good thing. Interestingly, there's an interesting point here that skipped historians. To me, this slope is not only proportional to CM alpha. In fact, it's proportional to the ratio between CM alpha and CM delta, which is related to the DC gain of the transfer function. That's the sensitivity. And the interesting point is that these engineers, they arrived at this metric without having access to this knowledge of the classical control theory and the concept of a DC gain. This was not available or well established at the time, so which points really to the engineering ingenuity of the staff. Equivalently, the stick force F is also proportional to the elevator deflection, so you can derive a similar expression for the stick force slope. It's also proportional to CM alpha or the ratio, the DC gain. So here's a curve for the stick force in the hands of the pilot versus speed. This is the cruise point. And if we, as you guys know, if we want to fly faster, this means that we need to push the control stick, and vice versa. If we want to fly slower, we want to pull the stick. And this slope is actually, is representative of how stable the airplane. The larger the slope, the larger CM alpha, and so on. One point here is very interesting, is that this means that for an unstable airplane, the things will be reversed, which means that for a highly unstable airplane, if you want to fly faster, you're going to pull the stick. That's quite confusing. So people at the time, they figured out this criterion to compare the stability of 2 given airplanes from flight measurements by focusing on this stick force curve. As you can see, here we have a considerable slope implying considerable stability. Here we have weak slope implying weak stability. So they describe this situation on the left as the elevators have no feel. So because the airplane may change its speed without requiring considerable change in the elevator deflection and the stick force in the hand of the pilot. So this is dangerous because the airplane may slip towards stall without the pilot feeling. So the claim was, or the desired characteristic was, it should be hard and difficult for the pilot to get the airplane into stall. It requires a large stick force. So that was the state of knowledge at the time, and then the community learned another set of lessons, which were nicely summarized in this paper by Otto Koppen. So he wrote the following. unfortunately, there is no direct connection between any of the possibilities named, these slopes that we have been talking about, elevator or stick force. There's no connection between them and the slope of the pitching moment curve, CM alpha. I mean, you say, oh, how is that? I mean, we see here clear that, you know, this slope is proportional to CM alpha, the same for the elevator deflection slope. What is he talking about? So he is referring to the following. Let's consider a tail unit, whether it's horizontal tail or vertical tail. The dotted line is the hinge line, okay? The solid red line separates the movable part from the non-movable part, okay? The movable part that is ahead of the hinge line, this is the dashed area here, this is what we call horn. This is what you have seen in the last problem of the last homework, which is due tomorrow. So you can design this horn. This horn actually affects considerably the hinge moment coefficient, CH delta. So you can design the horn to achieve whatever CH delta you want, of course within limits. So he mentioned that if CH delta is doubled, then this stick force will be doubled without any change of the true stability and control characteristics of the airplane. So he commented on this case. To the pilot, the slope of the stick force would be the same as though the center of gravity had been moved forward to double the slope of the pitch moment curve. He cannot distinguish between the two changes by the slope of the stick force curve. So that was a big issue. So he actually concluded that CM alpha being negative, yes, it's a satisfactory minimum requirement for longitudinal stability, but it's worthless as a criterion of measure of longitudinal stability. So I'm sorry, guys, to ruin the beautiful relation that we built throughout the course of CM alpha, I know, but that's what they found. In fact, he referred to a very interesting point, that the pilot affects the stability characteristics of the airplane. Because if the airplane experiences some disturbance, the pilot will, you know, instinctively correct for that disturbance, will not wait for the airplane to respond on its own. So, for example, if the airplane is experiencing the pitch up disturbance, the pilot instinctively will apply a corrective action, pitching down movement. And it's fairly reasonable to assume that the pilot corrective action will be proportional with the disturbance. If he or she feels a large disturbance, they will act accordingly, and vice versa. Now, if you add this additional pitching moment term to your equations of motion and get the eigenvalues of the fourth order polynomial, get the modes, long period and short period, and get the damping of these periods and plot them as the pilot corrective gain increases, you will find this. And 3 points at least are worthy of discussion here, very interesting. The first one, the pilot corrective action has a socialist nature. It takes from the rich, it gives back to the poor. So it takes from the strongly damped short period mode and gives to the poorly damped long period mode. So second, which is quite interesting also, this means that the poorly damped long period mode that people had worried about, it should not be of any worry anymore. Why? Because any corrective action from the pilot will provide good damping for the long period mode. This is why Köppen wrote, consequently, a lack of damping of the longitudinal oscillation is usually unnoticed by the pilot. And the result is that any pilot can satisfactorily fly anything that looks like an airplane. So the long period mode should not be of any worry. Third, the short period mode will decrease damping with the pilot corrective gain. So you may fly and you may design, as a designer, you may design a very good airplane, very good damping, large horizontal tail, everything, and then in the hands of the pilot, it loses damping. In fact, with a large pilot gain, this will go unstable. So this is why, not only that actually, there is the additional issue of the lag from the pilot. So if there is a lag in the pilot corrective action, which is inevitable, this will decrease damping even further. In fact, Köppen provided this interesting relation that the yaw damping, NR, the effective one after the pilot corrective action, is related to the original yaw damping, NR, but subtracted from it some term that is proportional with tau, the time lag of the pilot. And NR, as you guys know, this is the damping of the Dutch roll mode, which is of most concern to pilots and passengers. And Dutcher mode is also reasonably fast, so any loss of damping is of real concern here. So what we are talking about, or what is happening in reality, is really an interaction between airplane dynamics and pilot dynamics. So indeed, the handling qualities of the airplane is an interaction between the two. So this is nicely, expressively summarized in the seminal paper by Harper and Cooper. They wrote, "This then is the system, the pilot and the aircraft acting together as a closed-loop system, the dynamics of which may be significantly different from those of the aircraft acting without the pilot or open loop." This is why Köppen wrote, "Under these conditions, the stability characteristics that tend to complement the pilot in flying the airplane rather than that would allow the airplane to fly by itself. These are the important ones. The idea that the easiest airplane to fly is one that will fly itself was proven false many years ago. So we need the combined system." And he added, "Here is the source of fundamental problem in the study of handling qualities. The complete dynamic system is seen only by the pilot." That's the main issue, is that what is happening in reality here, which is the airplane dynamics and the pilot together, this is seen only by the pilot in flight. There is no way for the gentlemen or the guys at the design office to see the system. They see only the airplane dynamics. So that's the main issue. Vincenti wrote, this is why I wrote this, very interesting. He said, "There were good and bad airplanes, and pilot opinion could make or break a machine without the designer understanding why." Because you may, a designer may build an airplane, very good damping, very good horizontal tail, very good vertical tail, but then in the hands of the pilot, it performs completely different. And then the pilot comes back and say, "Well, this airplane doesn't fly well." And the designer has no clue whatsoever what went wrong. That was really a major issue in the community at the time. And this urged the community to seriously consider pilots' opinion rating to guide their design, to tell them how much stability is desirable. In the words of the test pilot, Goff, "There is no indication that stability of present-day airplanes should not be twice as great as it is." As you can see here, the tone seemed to have changed from stable versus unstable. Now we're talking about how much stability is needed. You can see this clearly in the late 20s, early 30s. Here are some quotes. "Instability in any sense is useless and unsafe. With the technical knowledge now available, there is no excuse for designing a machine of longitudinal instability." The famous Kelly Johnson, "The reasons why an airplane must be stable are more or less obvious. A moderately unstable airplane may be flown safely if the pilot continually manipulates the controls. However, this procedure is very nerve-wracking and tiring. Landing or takeoff is dangerous in an unstable ship. In flying blind, it's great comfort to know that if the controls are released, the ship will continue on its course safely, even in rough air." There was no single incident that led to the shift in the mindset of the community that we need stable airplanes. But you can see here, you can trace some of the reasons in Kelly Johnson's statement. Basically, airplanes' performance became better in the sense that they were able to do longer flights. So for the short time flights, the pilot can fly an unstable airplane fine, try to correct here and there, but he or she cannot continue for a long time keeping correcting for this. This will be exhausting. Not only that, also advancement in instrumentation allowed blind flying. And if you fly blindly without any visuals, it's really reassuring to know that your airplane is naturally stable. Also, piloting tasks became more demanding as time goes, in the sense the pilot role is not only to pilot the airplane and fly the airplane, but to do other peripheral tasks, precision bombing, mapping, photography, radio operations. So from every now and then the pilot is urged to leave the stick, do something, and come back. So Vincenti, concluded thus: what in 1910 had been controversial in 1920, at least arguable, had by 1935 become obvious, referring to the Kelly-Johnson statement. So the question now is that, yes, I mean, it's settled. The debate is settled. Yes, we need stability, but how much? So now the community is moving towards try to specify flying qualities requirement, specification. Yeah, okay, we now know that we need stability, but how much? How much, and we need guides for the designers, like what are the variables that the designer should shoot for? These are the main issues. One of the main incidents in this history was when United Airlines appointed Edward Warner to set specifications for this DC-4. Warner was the first chief physicist in Langley, was a professor at MIT, played a major role in the history of flying qualities. He played a very important role of a translator between different spheres, different communities, speak different language. Airplane designers from one side and manufacturers, from the other side airliners and research engineers at NASA, instrumentation folks and pilots, you know. So he set the first flying quality specifications for the DC-4, didn't put any limitation on CM alpha, but he put a limitation on dF by dV, the stick force slope, which we know is proportional to CM alpha. So now he's saying your airplane should not be stable, too much stable, right? And he set some requirements on the period and damping of the long period mode. As for the airplane responsiveness, he, mandated that the airplane should be able to pitch 5 degrees in 1.5 seconds at the minimum speed with stick force less than 75 pounds. So anyway, he of course, this is not all the requirements. He collected the knowledge at the time to set what he deemed to be reasonable specifications from his perspective. But another interesting incident, in my opinion, that set the history in this regard, when he was appointed as the chairman of the NACA's Committee on Aerodynamics. Now he has the authority to guide the research towards what he felt necessary for the community to move on. So in fact, in the exact same year, December of the same year, the committee released the research authorization under the title Preliminary Study of Control Requirements for Large Transport Airplanes. As you can see, this is really to help in setting specifications for airplanes like DC-4. People started quickly at NASA Langley testing 8 aircraft that ranged between 1,400 pounds to 6,000 pounds. The first report came out in 1936 by Sol. He actually, for the first time, asked the pilot to give grades. A grade A means high damping, high stiffness. A grade D means low damping, low stiffness. So this is the table. Another table for the stability, instability. S means stable, U means unstable. So this is where perhaps the first tabulated pilot rating, giving grades for airplanes. One of the interesting outcomes from this work was that the dynamic longitudinal stability characteristics as defined by the period and damping of the long period oscillation are not apparent to the pilot and therefore cannot be taken as an indication of the handling characteristics of airplanes. This is what we discussed before, right? So they now discovered that long period mode is of no concern. So Vincenti commented, the Langley work thus brought into doubt the 25-year preoccupation with the long period oscillation, at least so far as the flying qualities were concerned. Because the long period mode, as we discussed, is pretty natural. If you launch a model or a glider or an airplane, they all go through the long period mode. So, and when you see a mode as an engineer, when you see your device going through oscillations with small damping, your first reaction is try to enhance the damping of this mode. So indeed, the community was occupied for about 25 years, as Vincenti mentioned, with the long period mode, trying to enhance the dynamics of this mode, but turns out to be actually not needed, because any corrective action of the pilot would make it fine. R.T. Jones, in the very next year, he criticized, on the other hand, the dismissal of the short period mode. So you guys keep talking about long period, long period, long period. What about the short period mode? So they ignored it on the basis that it's too fast So the pilot most likely will not feel it in flight. It will not be observed, so they just ignored it. This is Artie Jones, quite a character. Let me tell you 20 seconds or so about him. He did not receive a formal education. In fact, at one point in his career, he was an operator of an elevator in a building. Not an airplane elevator, no, an actual elevator in a building, one of the Congress buildings in Washington, D.C. But he used to go to the Congress library, read about aviation magazines and NACA reports. So basically, he was self-taught. So let's see why he did not like this dismissal of the short period mode. He wrote, "There is an effective restraint of the machine against movements of the airplane in gusts. If we wish to make more practical use of the dynamical theory to analyze and predict the response to control the motions in gusty air, we cannot neglect this factor, which is of primary significance in these questions." So basically he's saying, you guys are neglecting the short period mode because it's too fast. Actually, it is the fact that it's too fast that we should care about, because it will represent the airplane immediate response to gust and pilot commands. So we should care about this. I really like his description of the short period mode as restraint of the machine against movement. Very deep understanding of flight physics and dynamical theory from someone who did not receive formal education, was self-taught. An inspiring story. So tests were intensified in the years to come. So Langley started now to expand, including 16 aircraft ranging between 1,000 pounds to 65,000 pounds. In fact, these 16 aircraft are on the cover page of Vincenti's book. These are the 15 aircraft, actually, out of the 16. So what happens here? One particular interesting incident happened with the Lockheed 14H, which is a popular transport at the time. The report came saying the degree of longitudinal stability is believed inadequate in many respects. The variation of control position and force is too small to give the pilot an indication of a change in speed. We discussed this before. So this airplane was weakly stable, small CM alpha, small stick force slope kind of thing. In fact, it also had unusually small short period damping, which was described by test pilots as very objectionable when excited by gusts. Guff, this pilot, he described it as very annoying and even unsafe. This airplane went into interesting oscillations, a specific mode that not all airplanes go through. In gusts, in turbulent air, the airplane goes into an oscillation, pitching, coupled with the elevator deflection. So the elevator was freely floating, all right? And now the airplane is pitching, pitch disturbance, the angle of attack. The airstream will push the elevator. It's because it's freely floating. And if the elevator moves up or down, it will change the pitching moment on the airplane. So we have a coupled motion between the pitching angle of the airplane and the elevator, the freely floating elevator deflection. And these oscillations were not adequately dampened. In fact, I created this very poor animation 4 years ago to represent this motion. The black stick is the airplane pitching up and down in an exaggerated manner. The red stick is the elevator deflection. Again, these were created 4 years ago. Now we have AI tools that hopefully should give us some fancy videos about this phenomenon. This is very similar to the snaking behavior that you guys saw in the last problem of the last homework. All right? Over there it was between yaw and rudder. Here it's between elevator and pitching. All right? This mode was not well damped. And actually, like in the words of Guff, it was unsafe and very annoying. In fact, it led to an accident one time. One time the airplane was rolling over the runway and it had a bump. So this bump led the airplane to become prematurely airborne and triggering these oscillations. Unfortunately, the airplane was too close to the ground and the pilot could not handle these lightly damped oscillations. It led to PIO, pilots-induced oscillations, which exaggerated or exacerbated the situation, led to a crash at the end of the day. So the community, they had to do something about these types of oscillations, which seemed to be very relevant to short period mode. Interestingly, there was no theory about dynamic stability for freely floating control surface. Like in this class, we did not discuss freely floating control surface, except for the last problem we presented as an educational problem in the very end. R.T. Jones came and said, yeah, I'll do it. So he rolled up his sleeves with Doris Cohen. Doris was his wife. And this report was the first NACA report with a female author, actually, which is very interesting. And this is a foundational report, for airplane flight mechanics with free control surfaces. They analyzed this coupled motion, 2 degrees of freedom, pitching, theta, and elevator deflection. They found 2 fast modes, faster than the standard short period mode. One is too fast, actually, with great damping. The other one is relatively faster than, is slightly faster than the standard short period mode, but it has small damping, and it actually shows this coupled oscillation between pitching and elevator deflection, which they observed in flight and described as very annoying and unsafe, and was the main cause for the crash that we discussed about. So this is why in the very next years, when people at Langley, Gilruth in particular, set the very first formal flying quality requirements, collecting the knowledge gained at the time, this report, which was released in 1941 as a secret report or classified report, it was declassified in 1943. And usually it's referred in the literature as the first generally accepted set of flying qualities requirements. So people, set some requirements for longitudinal, lateral, stalling, blah, blah, blah. Now they learned the lesson. No mention of the long period mode. It's of no concern to pilots. And instead, any short period oscillation with a free elevator should be dampened within 1 cycle. So this came out of this flight testing program. So Vincenti commented here, thus, in the end, the short period replaced the long period as the focus of concern for the designer. The importance of the 2 modes had become completely reversed. The background for this reversal, that is the quarter century in which the aeronautical community was blinded by concern for the long period oscillation, provides a cautionary example of how preconceived, uncritical use of mathematical theory can mislead in practice. It's a nice comment, but frankly speaking, I'm not sure if I quite agree with his phrase of uncritical use of mathematical theory. In fact, the mathematical theory, I don't think that this is the main reason. The mathematical theory provided both modes, the long period and short period, but then the community, they decided to focus on one and ignore the other. And, I think this is more related to the non-optimality of scientific discovery. In the sense, here the pioneering people like Lanchester, for example, when they observed these oscillations visually, they thought these are important oscillations. They're going to focus on these oscillations. So when the pioneers do something, then people come after them, and they just follow, taking things for granted without questioning the big picture. This is typical in the history of science. I mean, there are tens and tens of examples, and you find books actually written on this. This is one, The Invention of Science by David Wootton. Vincenti concluded, thus, by the early 1940s, the problem of flying qualities, though far from completely solved, was at least well defined. The road from the recognized but ill-defined problem of 1918 had been a long and complicated one. World War I or World War II pressures NASA to do more flight testing. They expanded to 60 airplanes of all types in this decade. And to do more systematic flight testing, a revolutionary concept came to help: the variable stability airplane, or in-flight simulators. These are airplanes like TIFFs, Learjet, Jetstar, maybe more recently Vesta. So the point is, if you want the pilot to try some specific short period characteristics and give rating, a grade, one option is you may look for an airplane that has these characteristics and let the pilot fly it and give rating. But instead, what they did here is that these airplanes, they have electronic systems which can change the feedback gains in flight. So in flight, they can change the airplane characteristics, and the pilot can try it and give the grade. Later on, these airplanes, they were actually used to simulate even new aircraft designs before flying these new designs. So imagine an airplane like the Vista, sometimes is acting like a fighter airplane, sometimes a bomber airplane, sometimes a transport airplane, sometimes even a space shuttle. It's very interesting. So in many cases, the shape and configuration of the simulator airplane may be very different from the airplane being simulated. Yet the pilot feel is the same because they make the airplane act like it. Very interesting concept, frankly speaking, and revolutionary. And then people realize, wait a minute, if we have a successful in-flight simulator, what about taking it to ground? So interestingly, the in-flight simulator was developed before the ground flight simulator, so which is quite interesting. And of course, all these concepts, they help to standardize pilot ratings like Cooper Harbor ratings. And eventually, all these tools, they help set very specific, very detailed military specifications for flying qualities, which evolved over the years, reaching the most recent one, which is the military standard 1797-8. Let's do some reflections before ending this lecture about the main difference between performance requirements and flying quality requirements. Because the performance requirements are precise figures, right? The cruise speed must be this much, ceiling altitude, range of the airplane, these are precise numbers. Whereas the flying qualities, they are just allowable ranges, right? They should be in this ballpark, right? Kind of thing. In fact, the performance requirements, these figures, they can be precisely measured in flight, and usually they are called performance guarantees. Sometimes, in fact, in many cases, they are written in the agreements between the airliner and the airplane manufacturer. So they can be tested in flight in a precise way. So here, these are just mere guide to the designer to hopefully produce a satisfactory airplane. There is no guarantee, right? So this is why in the language of Vincenti, he described this as objective ends themselves that the designer must meet, whereas these as objective means to a subjective end. Because at the end of the day, the final say is at the hands of the pilot. So this is why people say it's hard to think of another field except perhaps the auto industry in which the fate of a new design has been so determined by the skill, observation, and opinions of the testing staff. This is why Vincenti said, for these reasons, the aeronautical community learned to write performance specifications without the lengthy experience and deliberate research needed for flying qualities. He added that the balance between stability and control could not have been achieved on purely intellectual grounds and without extensive flight testing. That's very interesting. So engineers alone could have easily solved the stability and control problem. We can produce an amazingly stable airplane on its own, but in the hands of the pilot, that's a different game. So the engineers alone could have easily solved the stability and control, but not the flying qualities problem. The flying qualities, they required strong or considerable involvement from the pilots. I think we're done. I'm not sure if we should do the summary. We can do it quickly. The Wrights succeeded because of their focus on control authority, controllability in comparison to stability. Their airplane was unstable, both longitudinally and laterally. Actually, most World War I airplanes were unstable, so which triggered the legitimate questions. Do we really need stability? So this actually started a debate on the necessity of stability that lasted for a couple of decades in the community. Only with the emergence of high-performance airplanes and more demanding pilots' tasks, this triggered the need for stability. But the question was how much? And the main challenge was that the pilots do not feel the engineering metrics of stability in flight. In fact, pilots affect stability characteristics. So indeed, handling quality of the airplane is about the interaction between airplane dynamics and pilot. So this urged the need for correlating pilot's opinion with stability and control characteristics, which required extensive flight testing program. Many lessons came out, one of which was the long period mode is not important, and short period mode is the important one that must be adequately damped. A few hallmarks in the history, according to Vincenti, 1918 is the year where the recognition of the term flying qualities occurred in an official report. Between 1918 to 36, the committee was, dabbling their hands with what are the important parameters? Is it CM alpha? Is it the stick force? Is it short period, long period? By 1936, this is a milestone because this is where the United Airlines asked Warner to set the very first specifications, flying quality specification, DC-4. These were very preliminary, changed significantly afterwards. So between 36 to 41, the community was refining these requirements into, finally they reached, this is the very first formal report on flying qualities in 1941, declassified in 1943. So according to Vincenti, at that point, the problem was well defined. It's not solved yet, but it was well defined. And from that point onwards, it's just enhancement and getting new tools, better tools, more specific requirements, but no fundamental change of the type of the work. All right, so thank you so much. If you have any question, I'd like to take it.